Okay, subtractive color. Subtractive color space is going to be a little bit less intuitive for many people. You can think of these as colored pieces of plastic taking away light, but it also applies to surfaces and which light is getting reflected off of a surface. So here in this picture, we see an example with little pieces of plastic. So we have a yellow plastic film and a magenta plastic film and a cyan magenta. So this is color space is frequently called CMY, color space. And you may have heard about it for printing. And we'll see in a minute why is it that we want to use these colors rather than RGB for the subtractive space, but we do use these colors for subtractive space. If you want to get to red, green, and blue, then if we put yellow and magenta, then we can get to red in the subtractive space. So here's just a comparison, right? So here's color mixing with the name labels for additive color space, and here's the mixing with the name labels for a subtractive space. So what does it mean subtractive? Our whole spectrum of light comes in. If we have a red surface, this surface absorbs all the light except for the red light. The red light bounces off and goes to our eye. So this says the same thing. All the light's coming in, it's a red surface. If it's a white surface, all the light bounces off. If it's a black surface, it absorbs everything and no light reflects. By the way, why is blacktop hot? Because it absorbs all this light. That energy has to go somewhere. So it's all absorbed here. Why are white surfaces cooler? Because all the light reflects off, so they're not putting energy into this white surface. Right? So you can think of it this way. So here's inks for printing. I'm going to come to that K. I see there's people asking about K. I'll come to that. So when we print with inks, we print with lots of little dots. And so here's an extreme zoom in of our C, M, Y, and K dots of ink. And you can see they overlap each other. And so if I have, the light's going to come onto this white paper and it's going to reflect everything. But if I put some magenta ink, I'm now only going to be reflecting the wavelengths which pass my magenta ink. Right? I don't pass, so it's subtracting some of this ink is subtracting some of the color space. So here's a picture, right? So here's our CMYK space. Here's all of our dots, and you can and they overlap in space, but you can think of them as color channels: cyan, magenta, yellow. K is actually not for black. K is actually for key. I usually think of it as black also. Why is it named key? I don't know the answer. It helps you get deeper blacks on your page, and also black ink is cheaper than color inks. So we tend to try to use black to get better contrast and for cost expenses. So they expand it into this 4-dimensional space. The mathematical theory works with just 3 colors. So here's another way to think about reflection. So here's an object. Here's the spectrum that this object reflects. So if light comes in at, let's say this is 450 nanometers, we're going to reflect about half of it. If light comes in at, I don't know what this is, 550 nanometers, we're only going to reflect about a third of it. If light comes in at 750 nanometers, we're going to reflect 100% of it. So this is what the object does. Now we're going to shine some light on this object. So here's an incandescent lamp, and this is the spectrum of light coming from the incandescent lamp. So what's going to happen? Each frequency, right? I had 0.5 of light coming in, and then my rule says at say 550 nanometer, I go to 550 nanometer, I only reflect a third, so 0.5 times a third, so then we have a sixth of the light coming out. So these things multiply. So for the same object, if I change my light source to, in this case, daylight, I might get a different spectral curve coming off of this object, right? Because the light itself had a different spectrum. And so these might have different perceptual colors to them. So this is a subtractive operation, right? The object reflecting light is subtracting some parts of the wavelength. A lot of people have asked me a lot of questions about this and find it confusing. So I'm going to draw an idealized version that I find helpful to think about this. Why can't we use red, green, and blue for a subtractive space? So on the left here, we have additive mixing. So here's our whole spectrum, and I've just quantized it into 3 buckets. So a blue bucket, a green bucket, and a red bucket. We saw that real spectrums don't look like this. They don't have these square blocks to them, but conceptually, it makes it nice to think about. So if we add up all of the red, green, and blue buckets, we get the whole spectrum, and we've got white light. Now, what would happen if we had white light and we shined it through a red filter or on a red surface where everything else was disappearing, or a red ink? Well, we would get rid of everything except for the red part of the spectrum. And then if we put a green ink, it would get rid of everything except for the green part of the spectrum. So we'd multiply all this and we get black. So trying to mix RGB and subtractive space doesn't really work. We just quickly go to black, because anytime you mix any of these two channels, they counteract. So what do we have in terms of subtractive space? We're passing more of the spectrum, and we're just subtracting one block. So the cyan filter, remember cyan is blue and green with no red in the additive space, right? So blue and green is cyan in the additive space. So if we have a cyan filter, it just cuts away the red component. So if we take a cyan filter and a magenta filter, this cut away this component, this cut away this component, right? And the yellow is going to cut away this component. So we can just cut away one component at a time. So by doing subtraction, we can end up with something that's actually left over at the end. So this picture helps me a lot, thinking about what's going to happen when I mix CMY and what's going to be left over. I don't know if it'll help you, but this is a way that is useful for me to think about it. So let's look at a real world case of this subtraction. So some of you have probably heard that blue light is bad for a variety of different things. So I don't think there's well proven scientifically yet. All the articles that I've seen are kind of mixed. But some people believe that blue light causes fatigue when you're looking at screens. Some people believe that blue light keeps you up at night. Empirically, I find that to be true for me. And if you wear yellow glasses, they're supposed to cut away the blue. So what does a yellow filter do? So a yellow filter passes the red and the green and cuts away this blue component. Okay, and that's in fact what they advertise. If you wear our special yellow glasses, this blue part of the spectrum gets cut lower, right? And the idea is it's good for you in a variety of different ways. So this is a case that may help you think about what is this subtractive space doing. Conversion from RGB to CMY is very straightforward. This is just a linear operation, right? So CMY is just 1 minus RGB. So it's easy to go back and forth between these spaces. This is not right. I'm pretty sure K does not stand for black. I'm pretty sure K stands for key. I need to fix my